What's the topic?
Polynomial regression. Come on down.
How about quadratic?
Piece of cake, got this. Duh.
And the cubic thing?
Cubic in the bank. Duh.
Quartic?
No idea.
I don't know either.
Oh, breakfast?
It's your bread and butter, baby. What's your jam?
Greetings, Bio 6611. In this lecture, we're going to discuss the idea of polynomial regression, extending our linear regression model to account for higher order terms. We're going to start with the introduction of polynomial models and the general idea and motivation behind them. Then we're going to discuss how we can test for a lack of fit and identify the optimal potential number of higher order terms if we have a study design that includes replicates at the levels of interest. We'll then finalize our discussion with some points about hierarchical modeling and the potential issue of collinearity when dealing with polynomial terms. So let's start by introducing the idea of polynomial models. Mathematically, we can generally think of this as a kth order polynomial for one variable x. It can be written in a way that looks pretty similar to a regression equation. We might say y equals some value c naught plus c1 times x plus c2 times x squared, all the way up to that kth term, that kth order polynomial, ck times x to the kth. In this case, k has to be a non-negative whole number, and the c's represent some constant value. Again, this is pretty similar to what we might do for a statistical model like we see written out here, where we have our outcome y. We then have a true regression equation where we have an intercept beta naught plus beta 1 times x, then plus beta 2 times x squared, that quantity squared, up to the kth power. And then we have, of course, our little plus epsilon, because here we have the true regression model, where we still define the assumption that the errors are distributed normally with mean 0 and some common variance, that homoscedasticity assumption. One important thing to note that may seem a little counterintuitive, especially as we see some examples moving forward, is that the statistical model we're talking about is still a linear regression model, because the y is a linear function of the betas, even though the predictors have this polynomial trend or relationship. Where are some cases where we might find use for polynomial models? Well, one obvious case would be where the analyst or statistician knows that a curvilinear effect would be present in the true response function. If we have some background information about some scientific response, perhaps we know to start right away with some sort of polynomial trend or relationship. Also, as approximating functions to unknown and possibly very complex nonlinear relationships, polynomial models can be better at approximating those than just a straight line linear regression models that we've frequently spoken about so far. There are some important considerations that we'll touch on throughout this lecture, including how we select the order of the model. In other words, what higher order should we have? Should it just be a square term with a quadratic model, or should it be a cubic model with the power to the third, quartic, or so on? We'll also discuss and point out towards the end some of the ills of extrapolation and why it can be challenging to deal with, as well in general of ill conditioning of the models. To help motivate this though, we're going to build off of our linear regression framework on this example from one of our textbooks for the class, the KKNR textbook. In the book, they have a laboratory study dataset which was undertaken to determine the relationship between equally spaced doses X of a certain drug, and weight gain has the outcome y. 24 total laboratory animals of the same sex, age, and size were selected, and then the 3 animals were randomly assigned to each dose group. The results from the study are summarized here in the table below, where we see that each dose level 1 through 8 has those 3 measurements from our 3 different animals. We can also see the relationship of weight gain over here at the right hand side, and we see that we have our linear regression fit here drawn on that figure right now. And from first glance, we might say it's not a terrible fit, but it does seem like there's some other relationship going on here, potentially something more polynomial in nature that the linear regression is not quite addressing. Let's start by focusing on the model that doesn't include any polynomial terms. In other words, a simple linear regression model for that straight line fit. The first thing we can note is that we do read in our data or create a data frame based on the information from the table on the previous slide. We then fit our simple linear regression model for the outcome of weight gain with the single predictor for that dose level. And then we look at the summary for our coefficients here below. We can interpret these as we normally would, where the intercept is the predicted weight gain when the dose is equal to 0, which would be negative 1.35. However, this is extrapolating beyond the range of our data, so it's not really a meaningful interpretation. Likewise, for the slope, we can interpret it as we normally would. There is a significant association in this case, because p is less than 0.001, between the dose and weight gain, where for every 1 unit increase in dose, for whatever the generic units are for that, weight gain increases by 1.11 units, with a 95% confidence interval of 0.96 to 1.26. So we see here with this model, we actually have a very standard interpretation, but as we noted on the previous slide, this may not do the best job of describing that relationship. In fact, we can look at some of our diagnostic plots, and one that will scream that something is off is the residual plot. Here we're looking at the jackknife or studentized residuals on our y-axis compared to our predicted value y hat. And so what we see here is that the regression points that we have for the residuals don't follow a random pattern scattered around that horizontal line here at 0. What we actually see in this case instead is a very decidedly parabolic sort of pattern or shape. So what we can ask ourselves the question of is, does this straight line model fit the data based on this residual plot? And our answer should be a resounding no. It does not do a great job of fitting the model. However, we could explore, unsurprisingly for this lecture, some form of a quadratic or higher order term model. The most sort of intuitive next step would be to add a quadratic term, or to the power 2. So a few ways we can do this that just I think are useful to highlight. One is that we can define the squared term as a new variable in our data set. For example, create a dose2 variable, which is dose squared. Then we can fit a model with the LM function for our linear regression, where we just add that term in. Alternatively, we can also define this directly within the function itself, but we do have to be careful with different functions. And in this case, we have to wrap it in this I function to tell R that in fact we do want to use it as it is with the dose squared. With that though behind us, we can imagine or take a look at some of these plots to see what we have. And the first thing we can note is that we have a much better fit. The dashed line here is our quadratic term for the model fit, and we see that it does a pretty great job of actually going through those points throughout all the dose levels. Likewise, we see that our standard studentized residuals, our jackknife residuals here, are much more equally scattered about that line 0. There doesn't seem to be as much of an obvious pattern, at least, suggesting that it does seem like adding this squared term, this quadratic term, is beneficial to improving the fit of our linear regression model. We can also just take a look at the summary of the output from the LM function here, just to get an idea of some of the things that we're going to use later on. But one thing we can note is that here in our coefficient table, all of our p-values are significant, including the added term for dose squared. We can also note, and we'll see this as well for a side-by-side comparison in a moment, that the beta coefficients, of course, have changed for the intercept and the dose because we've added another term to the model. Another thing that we can highlight or draw from this summary table is our F statistic and p-value, noting that it is less than 0.05 for the p-value. So overall, the model does seem to be better than just using the average for weight gain alone. Taking the dose information, when also dose squared in this quadratic model, is beneficial. So this leads us to two questions we may want to spend a second thinking about and answering based on the data we have so far. The first is the overall regression model significant? That is more of the variation in our outcome y explained by the second order model than by ignoring x completely and just using y bar? One of the tools we've learned so far to use to answer this question would be our overall f-test. And we can note here as well that we had that information on the previous slide, where we can go back, or we can just note f was equal to 5,247 0.78, and the p-value was less than 0.001. Therefore, we would reject the null hypothesis, like we said on the previous slide, and determine that this model is significantly better than just using y bar. A follow-up question we might want to ask, though, is does the second order model actually provide significantly more predictive power than the straight line model? We're obviously adding some more complexity by adding another predictor to the model. So, is that worth the trade-off of having that increased complexity, or can we use the simpler, more parsimonious model? Now, in this case, we could do a partial f-test, but we can also note that we have from the coefficient table that t-test information automatically provided, just to test this one specific addition of a variable relative to the existence or presence of dose alone as a non-quadratic or cubic term in the model. What we see here, if we were to look back on this previous table, is that the t statistic was 29.46 for our dose squared term, and it had also a p-value less than 0.001, so a very small p-value. In this case, we would say yes. In fact, we reject the null hypothesis that beta 2 is equal to 0, and it does seem like the second order model, that addition of the quadratic term, is significantly more predictive than just the straight line model alone. We can also draw a couple points or considerations from comparing the ANOVA table and coefficients between our two models. The first thing we can note is that what happened to our beta coefficients? Well, we see that, for example, the intercept went from being negative in model 1 to positive in model 2. We also see then that x1 for our dose term on its own went from being positive in model 1 to negative in model 2. So essentially, the coefficients changed based on the presence of additional information in the model. And part of the reason we see such a drastic change in this case is because our x squared term, our dose squared term, is significant to improve that prediction of our model. One way we can see that is that our MSE went from 0.653 in model 1 all the way down to 0.016 for model 2. This describes a much better model fit with less variability that's unexplained by the model as we've provided it to be fit. This leads us to one question, though, of should I add even higher order terms to my model? I mean, given that the second order model was more appropriate than a straight line model, shouldn't we just keep adding higher order terms to that second order model, make it a third, fourth, fifth order model? The first thing we can note is that it is possible that adding higher order terms could be beneficial, but we have to balance this with our consideration of trying to identify that parsimonious model. Again, it's helpful to identify something that fits the model or the data the best, but also if it's overly complex and we can't use it in any practical terms, then maybe we need to reevaluate all the assumptions that we're putting into the model and what we're trying to achieve. However, we also know that we don't have to just willy-nilly hope for the best. We do have statistical approaches that we can consider, and some of which we saw previously, such as using the partial f-test or a t-test or the overall f-test to evaluate the potential utility of a model. But we should not rely only on a low p-value in this case. Just because the p-value, let's say, was less than 0.05, does not necessarily mean that we have the best fitting model or the most intuitive. We should also examine things like the residual plots and the context of our problem. That will help us to visualize if it seems to make sense. And in cases where we have replicates at each level, we have additional tools and tests we can do to further break down this question. And so that leads us into our next section of testing the lack of fit in the context where we have a design with replicate or multiple measurements for each level that we're interested in trying to compare. Recall from before when we defined the mean square error. We use that to come up with our estimate of sigma squared y given x, or the variance of y given our predictors x. We previously noted in the context of simple linear regression, we have this framework for our formula where we can take the sum of our observed outcome minus the predicted outcome squared divided by n minus 2. However, we also know the MSE will only provide an unbiased estimate of the error variance when the hypothesis model is correct. Otherwise, our estimate will be larger or inflated relative to the true variance. And if the model is incorrect, we actually have two different potential sources that may be contributing to this inflation of the sums of square error. One is what we call pure error. That's the true variability in our outcome y. That's something we can't address. That's just what is present in the data naturally. The second one, though, we can address. It's the error due to a fitting an incorrect model, or a lack of fit error. This is something we can improve by choosing a model that's more appropriate or includes extra covariates or quadratic terms, polynomial terms, to more appropriately model the data. Fortunately, in the case when we have replicate observations, we actually can formally test for this lack of fit, whereas normally we have to sort of evaluate it graphically and determine just based on our knowledge and context what may or may not be appropriate. It is possible to estimate the pure error by calculating by hand. Now in practice, we're going to primarily, if we do this, use computational software, but it is worthwhile to note the process we could take. For example, we would first calculate the average weight gain within each dose level. With that information, we would then calculate the sums of square for the pure error as each observation minus the mean for the dose level squared and sum it up. And then we would look at taking the sum of those terms and the overall degrees of freedom we have within each group. One thing we can note here is that at each level the degrees of freedom is equal to 2 because we have to estimate the sample mean for those 3 doses, and so we have 3 total observations, but we take away one of those degrees of freedom for estimating the mean. We then see, though, our calculation here is then simply taking each of these estimates and taking 0.26 divided by 16 for our mean square due to the pure error. We can then use this information to calculate the improvement or lack thereof for different models. For example, to test the linear trend using the pure error and the model 1 results we had before, we can take the information we had for the estimated beta hat dose and its standard error, as well as its mean square error from our ANOVA table, and we can then plug in the pure error we have above. We put them all in over here, and we see that we get an estimate of 97.87. Our previous t-statistic for model 1 was 15.44. So we can note here as well the variance was 40 times higher due to the lack of fit error from the straight line model. However, again, we will generally not do that type of calculation by hand. Instead, we can do so by a special coding structure and fitting a model. For example, we can fit what we call a saturated model, or a model that includes a dummy code for each level k of x. So for example, we can induce this structure by using as.factor for our dose variable and weight gain, and then we can extract the coefficients from this linear regression model, which we're calling LM_pure for the pure error. What we see here is that we do have, with the intercept representing the case where all of our indicators are 0, so it's the mean for dose 1, we then have the difference for each dose level 2, 3, 4, all the way up to dose 8 for how it differs from dose level 1's mean weight gain. We can also then use our ANOVA function to calculate that we've introduced previously to calculate an ANOVA table. Here we then see we get the same approximate estimate for the mean square error of 0.016. So it can be much more efficient and quick, especially if we don't have a small data set like we do in this case, to just use this coding structure to then get this pure estimate of the error from the mean square and the ANOVA table. With this information, then we can look at the lack of fit. The difference in the regression sum of squares between the lower order model being considered and the full model containing all higher order terms is what we call a lack of fit sum of squares. This specifically can be used to look at a lack of fit test statistic, which is going to be based off of our good friend, the partial f-test. In this case, it has the exact same setup, but our full model is going to be that saturated model we saw on the previous slide. And the reduced model will be whatever model we're looking at for the number of higher order terms we wish to evaluate. Just for our reference, we have the definition that we had before for these terms, where n is the number of observations, p is the number of independent variables that are in whatever our reduced model of interest is, and k represents the independent variables we removed from the full model, or the higher order terms we're not using. The reason this is a useful shortcut with the coding we saw on the previous slide, even though that saturated model technically had nothing to do with our higher order terms is that the sum of square error of the highest order polynomial model will be equivalent to the sums of square error for a model including a dummy variable for each dose level. In other words, we can use that as a shortcut to get the information we need to conduct these lack of fit partial f-tests. Let's start by looking at using that partial f-test for a lack of fit to evaluate our straight line model from before. In our example, the highest order polynomial we could in theory fit is up to the 7th power. This can be calculated as the total number of dose levels we have minus 1. Using this, then we would be testing for our straight line model, the null hypothesis, that all of the possible higher order terms that we could have are all equal to 0. In other words, that x squared up to the x to the 7th term are all equal to 0. Based on the ANOVA output and tables we had before, we can then extract that information to conduct our partial f-test. And here we see that we would have 6 terms that we're removing from the model, that full model with 7 power, up to our straight line model with only the first power term or first order term. And we see that we get a statistic of 144.75. We can then compare this to the F distribution with 6 and 16 degrees of freedom based on our given data set and the model we fit to get a critical value and a p-value. In this case, the critical value will be 2.741 and our p-value will be extremely, extremely small. Since p is less than 0.001 and f is greater than 2.741, we would reject the null hypothesis pretty resoundingly. In this case, at least one higher order term is probably not equal to 0 based on this lack of fit that we've described with our partial f-test. A natural question would be, maybe the quadratic model we fit by adding that term with the 2nd power is a better fit, but potentially maybe we need even higher order terms yet. In this case, the hypothesis that we're testing for the quadratic model would be the cubic up to the septic model terms for beta are all equal to 0. In other words, it's not worth adding any higher order terms because our model is adequately described with the quadratic model here with that 2nd power. Again, taking the information we had on the previous slides, we can first note that in this case we have 5 values, the 3rd, 4th, 5th, 6th, and 7th terms that are removed from that full model with the highest order possible term. And plugging in our information, we see we have a much, much smaller f statistic of 0.98. We can compare this then to our f distribution with 5 and 16 degrees of freedom to calculate a critical value and a p-value. Here we see that the critical value is 2.852 and our p-value is 0.46, so much larger than 0.05. In this case, because p is greater than 0.05, or correspondingly our f statistic is less than the critical value 2.741, we fail to reject the null hypothesis. This suggests no higher order terms are needed, and that the quadratic model has what we might think of as the best fit for the data we have. So that wraps up a way we can evaluate the special case when we have these levels that have replicates or just multiple observations within each level. We can also close with a few notes and considerations for our hierarchical modeling more generally and how to potentially handle issues with collinearity. One thing to note is that what we've really been fitting are hierarchical models. For example, if we consider just that polynomial model of order 2, our quadratic model from before, we have this set up for our true regression line. Now suppose we fit the model though and we look at our estimated coefficients for beta 1 hat and beta 2 hat, and we determine that beta 1 hat is not significant, but beta 2 hat is. In that case, we may want to identify a more parsimonious model, so perhaps we would remove the beta 1 hat and x term. In that case, we would now have this y equals beta naught plus just beta 2 x squared plus epsilon. Seems pretty benign. However, suppose we then were interested in estimating how a shift might take place and what that would do to our outcome. For example, if we added some constant z to the predictor x. Well, if we plug that into this simple reduced model, what we actually end up seeing here is that we get this much more gnarly looking equation, where we've now reintroduced here just our x term on its own without the quadratic power. This first order term has now reappeared, and so our model has effectively changed since it is not going to be equivalent to what we see at the top here when we have the full model that has both x and x squared. In general, location changes should not be making any important changes to the model, but in this case, an additional term has been added. For this reason, we should not remove lower order terms in the presence of higher order terms. In other words, we really don't want the conclusion to depend on the choice of the location we're observing at. And for that reason, if we identify a higher order term is appropriate, even if the lower ones are not significant, we should keep them in the model. We can briefly take a look at this quadratic and cubic even terms for the FEV example we've worked with in other lectures. In this case, we can see how our relationship with age and FEV are fit with the straight line model, a quadratic polynomial, and a cubic polynomial. We've also shown here in the bottom right the quadratic term when we remove that first order non-quadratic predictor for age. What we can generally see is that it does seem like the straight line model is probably a decent fit. The quadratic model does seem to maybe be going a little more closely through our points since there is some sort of pattern maybe to the data. And in fact, the cubic seems to really be doing a solid job, except for the fact we have this concerning behavior up here where it starts to decrease, and also towards the end of the tail here, which would, even though we're extrapolating, suggest an increase. So this would be a great example where even if we actually evaluate these models statistically to identify what's best, we may still have to consider the consequences of the model, especially at the tails. And in this case, the cubic polynomial might not quite make the cut. We can also just briefly note that by removing that first order term, we have our red model here for the quadratic, but then it kind of flips itself, almost the relationship in this case, where now with it removed, we now have this upward sort of facing curve. So again, changing the behavior in ways we maybe wouldn't necessarily expect or think are ideal. The final slide we're going to end on is noting how to potentially address certain collinearity problems. We know that we can have issues with multicollinearity in polynomial models because we've just added the variable with itself squared, cubed, or so on to the model. And this can make certain evaluations of statistical significance challenging or seem counterintuitive. There are two possible solutions. One is specific to the case of just looking at a quadratic or second order polynomial model, but we can center the predictors if we're only interested in comparing the first and second order model, because this will remove the collinearity in that case. However, if we want to look at even higher order terms and we are worried about collinearity, there is a family of orthogonal polynomial contrasts that can be used and extended to these higher order comparisons that does remove the collinearity. However, this is a bit beyond the scope of this lecture set, but we do provide supplemental notes on this topic for your own information. However, it will not be on the homework or the exams. And with that, we'll conclude our discussion of polynomial regression models and move on to look at interaction terms or effect modification.